Thank you, Professor Kudla, for the introduction. I'd like to take this opportunity to thank the organizers for giving me this opportunity. So I'd like to discuss parameterization of rings of finite rank, but with a geometric perspective, which sort of boils down to looking at M-fine rings. And we'll discuss weakly resolved rings, which is sort of a subset of M-fine rings. So we'll sort of try to understand this in the context of Marley's conjecture and arithmetic statistics. So let's define Sxn to be number fields k of degree n such that the Galois closure of k is Sn and the discriminant of k is less than x. So ever since Hermite, I think Hermite showed that summation Sxn is finite. And since then, the asymptotics of this particular set have been of interest. So you define nxn to be the number of elements in Sxn. And Marley's conjecture applied for the group Sn basically tell you to expect that nxn should be asymptotically equivalent to some constant times x. This constant is very explicit. And yeah, the actual conjecture is very old, especially for general fields. Yeah, so the progress so far has been n equal to 3 was finished, n equal to 3 was done by Davenport and Heilbronn, n equal to 4 was done by Bhargava, and n equal to 5 was done by Bhargava. There is no progress beyond this. And there are few main difficulties that come up in actually approaching this question. First is perfect parameterization theorems. To actually count number fields, you sort of try to always move to more concrete arithmetic objects. This can be polynomials, binary forms, or something of that sort. And so parameterization theorems are sort of something that allow you to move from, let's say, a ring to a particular form. Right? So for n equal to 3, we have the Levi's theorem in Delon for these famous monographs, the irrationalities of degree 3, that associate a binary, that associate to every cubic ring a binary cubic form. And sort of the form is so associated that under GL2 action, the ring remains invariant. And this under GL2 orbits, this is a bijection. This is a bijection. And for n equal to 4 and 5, we have Bhargava's stunning parameterizations of quartic and quintic rings. And the second problem that comes up is sieving. For n equal to 3, this was handled by Davenport and Heilbronn. N equal to 4 and 5 was handled by Bhargava. So in general, even lower bounds on nxn is sort of a new phenomenon. Before these recent two bounds, I think the previous bound was x½ plus 1 over n squared. So in 2019, Bhargava, Shankar, and Wang show that nxn is greater than x½ plus 1 over n. Let's call this result A. And in 2022, Bhargava, Shankar, and Wang show that nxn is greater than x½ plus 1 over n minus 1. Let's call this result B. So result A, the parameterization behind result A is sort of based on a concept known as monogenic rings, which is a simple concept. For us, we will try to limit ourselves to integral domains. So a monogenic ring is a ring isomorphic to Z of alpha for some alpha is in Z, for some alpha is in Z bar. Right? So naturally, you have to a monogenic presentation of a ring, you have a naturally associated monic polynomial. So this sort of and this is clearly a discriminant preserving association. And this allows you to move from counting number fields to counting polynomials of a certain type. And clearly f of x and f of x itself will give you the same ring. Z of alpha is same as Z of alpha minus n. So result A is based on this map. And it's based on two facts. One is 100% of the translation orbits give you distinct rings when you look at polynomials as ordered by height. And the second and the more important, the difficult part was sieving out unwanted elements in the parameter space. So this would be sieving out monic polynomials that do not correspond to full rings of integers, sieving out those polynomials that correspond to number fields whose Galois group is not Sn, etc., etc. So result, now let's move on to result B. Result B is based upon a parameterization that we like to call binary rings, that's known as binary rings. So let f of x comma y denote a binary form, a n x to the n and so on. And for the sake of convenience, let's take an not equal to 0. Let delta denote the image of x in the algebra q of x modeled by f of x comma 1. And so we define Rf to be the z span of 1 an delta square an minus 1 delta, and so on. So the kth term will be something like this, and that's the last term. So this is a very classical theorem that Rf is always a ring. So Rf is known as the binary ring associated to F. So again, you have binary ring allows you the concept of a binary presentation of a ring allows you to move the counting of number fields from rings to binary forms. And this is again a discriminant preserving map, which can be easily observed from the previous slide. The discriminant of this will just be an to the 2n minus 1 times the discriminant of delta, which is just the discriminant of f. Okay? And you will have f of x comma y and f of g will give you the same ring for any g in GL2. And so result B would be based upon the fact that there is a cone in sort of the appropriate space in which no two forms correspond to the same ring. And the harder part is sieving out unwanted elements in the parameter space, which I'm handling for this part of the talk. So parameterization challenges. The thing is, these parameterizations can only get you so far because we actually expect the number of number fields whose ring of integers is monogenic and whose discriminant is bounded by x to be about x to the half plus 1 over n. Similarly, we expect the number of binary number fields or number fields whose ring of integers is by a binary ring to be about x to the half plus 1 over n minus 1. So these parameterizations can only take you so far, and thus we need sort of more general parameterizations to improve the order of x in the lower bound for nxn. And this is sort of very obvious in places where we do know an appropriate bound. For example, n equal to 4 and 5, where you have a very different parameterization, which allows you to get much further. So then we can come to the concept of weakly divisible polynomials. So we say f of x in z of x is weakly divisible by m at L if m square divides f of n and m divides f prime of n. So in fact, most of the result A and result B was actually about bounding these types of polynomials. These types of polynomials are polynomials that cannot be easily handled by the Ekadal sieve. And therefore, they pose a significant problem because they come into the error terms first off. And because they come into the error terms, they are not easily handled by Ekadal sieve. So they need a special approach to handle them. The way they actually handle it is they embed the space into a larger space where this particular condition turns into a condition that can be easily handled by Ekadal sieve. So what we define is we define R prime of f comma m to be the z span of basically the same thing except for an m at the end. Okay? And we show that if f is weakly divisible by m at 0, then R prime of f comma m is a ring with discriminant of f over m square. Oh, the Ekadal sieve? Yeah, Ekadal sieve. So Ekadal sieve is a sieve that allows you to sieve out elements that lie in a codimension 2 subspace for every locally. So locally, that allows you to remove elements as long as they lie at least a codimension 2 subspace with respect to your parameter space. So using this particular parameterization, we show that the number of rings of rank n over z with discriminant less than or equal to x is about x to the half plus 1 over n minus 4 by 3, slight improvement. And using the tail estimates in the paper of Bhargav Shankar, which sort of established the current best lower bound for nxn, we show slight improvements for n odd. We show x to the half plus 1 over n minus 1 plus 1 over 5 n to the 4 plus something small. And for n even, we show x to the half plus 1 over n minus 1 plus 1 over 18 to the 8 n to the 9 plus something O of 1 over n to the 10. So an interesting consequence of this, when you combine it with Wallin-Widmer's result, is there exists infinitely many number fields with no small generators. Basically, if you look at any polynomial that is weakly divisible by a very large element, that and it corresponds to a number field, then those particular polynomials will actually denote number fields which don't have a small generator. So it sort of conclusively answers the famous Rupert's 1998 question. And so we developed some alternative sieve techniques. Instead of looking at SX number of elements in SXN, if we actually instead look at this particular weighted sum, we can see that the Mallay's conjecture for Sn is equivalent to n star xn is twice Cnx to the half. And using we can show that using these alternative sieve techniques that n star xn is greater than x to the half, x to the 1 over n minus 4 by 3 minus epsilon. So basically, you do get the appropriate lim sup. You don't get the appropriate lim. So basically, let's see how far this concept of weakly divisible rings can take us. So using optimized sieving, using the actual setup rather than just the tail estimates, in that particular paper, we expect to get x to the half plus 1 over n minus 4 by 3 under what we term as injectivity conjecture, which we'll explain later. We are able to get x to the half plus 1 over n minus 3 by 2. And under what we like to call an equidistribution conjecture combined with injectivity conjecture, we are able to get x to the half plus 1 over n minus 5 by 3. We are still nowhere approaching 1. So even this particular parameterization is quite lacking. Okay. So let's put this all information in some context. So let me remind you, a monogenic ring is a ring of the type Z of alpha. And binary ring can actually will show a slightly different representation, a geometric representation. When f is a primitive binary reducible form of degree n, so that if delta comma 1 is 0, then the binary ring associated to f can actually be written as z of delta intersection z of delta inverse. Right? In fact, you can also show that the ideal class generated by 1 comma delta is always invertible in this ring. And both the ring and the ideal class remain invariant under the action of GL2. This can, for example, if you restrict this n equal to 2, then this particular theorem can be seen as an equivalent to Gauss composition. You can actually see Gauss composition from here. So it's sort of a nice general theorem, geometric theorem that captures all of these things. It's a classical theorem. And let's look at now Bhargav's classification of quartic rings from a geometric viewpoint. So what does Bhargav's classification of quartic rings say? It says that if you take pairs of ternary quadratic forms, to each pair of quadratic forms, you can associate a quartic ring, and a corresponding cubic resolvent ring, which is made to through a certain map, which we are not going to bother with at this point. And this particular map is a bijection. So Wood, Mellin-Matchett Wood shows that this particular ring associated to R, F, comma, G can be seen as the ring of functions of this projective variety in a paper where she ports this whole system to a general scheme. So a small computation from here shows that for primitive pairs F, comma, G, if one alpha beta is sort of the degree 4 point cut out by these F and G because they're two quadratics, then R, F, comma, G can be seen as Z alpha beta intersection Z alpha inverse beta. And so now this is interesting because weakly divisible rings can also be seen in this particular form. So when F is a primitive binary irreducible form of degree n with f of delta comma 1 equal to 0, and let's say f is weakly divisible by m at 0, then just using the previous binary ring fact, you can see it's not very hard to see that r prime of f comma m can actually be written in this form. And if we set alpha equal to delta and beta equal to this m times f of 0 over m square over delta, then r prime of f comma m can be written as this particular form, which is the same as the previous form. And so you can see where we are trying to go from here. And so let's put this in context. Let's define D4 L inverse to be degree 4 points in P2 Z bar, such that they satisfy no linear relationship over Q. And let's define DN Q L inverse to be degree n points in P2 Z bar such that they satisfy a particular quadratic relationship of the form xy minus az square. Okay. So under these definitions, we can see that monogenic rings come from A1 Z bar. Binary rings can be seen as information about points in P1 Z bar. Weakly divisible rings can be seen as information about some subset of P2 Z bar in a universal way. And Bhargav's quartic rings can be seen as information about similar rings, but degree 4 associated to degree 4 points. So the data about the ring of integers of Q of delta. So we know that every field can be written as Q of delta for any delta, for some delta. So let's try to understand how the data of the ring of integers of Q of delta is organized in terms of the binary form. So you have the ring Z of delta intersection Z delta inverse, or appropriately Z of alpha when alpha is integral. This particular ring discriminant varies nicely and neatly continuously with the coefficients of the binary form of F, binary form associated to delta. Okay? And then after that, you have the index of this above ring in the ring of integers. And this information is only available to you locally. So this means that if you want to determine if p to the k divides the index, you will have to look at the form modulo p to the 2k, and you will get information based on looking at the form modulo p to the 2k. Right? So what sort of what moving from P1 to P2 allows you to do is it allows you to push part of the index data, which will be very haphazard with respect to, let's say, the coefficients of delta, into a continuous form, provided this ring is a subring of that, the larger ring that you're looking at, which when happens is something we'll discuss later. So if you look at this particular table, by moving from binary rings to weak, let's say Bhargav's quartic rings or weakly divisible rings, part of the data that we are part of the data is available as an index, you are able to push it into a continuous form by allowing you a much larger set of coefficients and much larger set of coefficients, basically. So we come to our objects of study, M-fine rings. You really don't need the -0, but for sake of simplicity, let's assume alpha and alpha to alpha m are algebraic numbers. Let k denote the number field given by q of alpha and alpha to alpha m. Then you know that this particular ring, which is sort of the equivalent of the previous z of alpha beta intersection z of alpha inverse beta and beta inverse alpha beta inverse. This is always a subring of OK. We refer to this as an M-fine presentation of a ring. Then we can show that this particular ideal generated by 1 alpha 2 so on alpha m is invertible in the above ring. And we can show that, let's define an admissible pair, which is basically a ring of finite rank along with an ideal class in the ring, invertible ideal class in the ring. And we can see that the above admissible pair, ring, ideal class, is invertible under the natural action of PGL m plus 1. So let's put the classification of rings, classification of quartic rings into this particular language. So what it says is, it says something more about the rings that can be written in that particular form. It says that every quartic ring, every quartic primitive ring, primitive is a very specific property that we won't go into. It's not too hard to define, actually. Every quartic primitive ring of integers occurs exactly once. Actually, every quartic primitive ring occurs exactly once in the GL3 orbit of two fine rings. Right? Yes. Oh, so M-fine ring is, this is what we call an M-fine presentation of the ring. So a two-fine ring would be any ring that can be written in this form. I mean, forget this. Any ring that can be written in this form will be a two-fine ring. Yes, yes. No. too far. My bad. I should have kept the notation consistent. Okay. So Bhargava's classification of quartic rings talks about injectivity and surjectivity of the corresponding map, is what I'm trying to find. So sorry. Yes, yes. That is what the theorem is. It's an injective and surjective theorem on primitive rings. And so it's worth considering something interesting that happens for quartic rings, and that is yeah. Yeah. So every degree 4 points in, let's say, P2 Q bar will either be an intersection of two quadratic rings or two quadratic curves, or a 1 degree 1 curve and a degree 4 curve. This neat kind of a structured sort of where every possible thing that can happen happens in sort of that what can be seen in the context of Bezout's theorem does not necessarily happen for higher degrees, which is a point of contention. And the hardest part about this would be the notion of primitivity, which Bhargava gives. Generalizing that notion is sort of a slightly difficult part. So in this particular context, you can show that the notion of primitivity given in Bhargava's paper translates to the ideal generated by f comma g in zxyz is a prime ideal. So whenever it's a prime ideal, we can say that the pair f comma g is primitive. That's one way of looking at it. So properties of an M-fine ring. So we'll sort of change notation because we have the invariance under GL M+1 action. So let K denote the number field given by Q alpha 1 alpha 2 alpha M. Let L denote this particular Z module. Then SL, which is defined in this, SL can be defined in this form because it's independent of the coordinate choice. And for finite modules, L and L star of K, we define these two things, L colon L star to be elements in K so that XL star is in L. And we define O of L to be endomorphisms of L basically. So as a theorem, we show that SL is actually this particular limit of rings. This is a series of increasing rings that is bound, which are all integral because they fix a finite module, and therefore they are bounded above by OK. And so we show that SL is this limit, and because of this, we are able to show a theorem that does not seem that I cannot find in the literature anywhere. It's an interesting theorem on its own, that this particular M-fine ring is the smallest order in which an ideal generated by the tuple 1 alpha alpha 2 alpha M is an invertible ideal. So this means that any ring in which R plus R alpha 1 plus R alpha 2 so on R alpha M is invertible must contain this ring. Right? And this is what we like to call the generalized composition law. This says that SL times SL star is SLL star. So when L is equal to L star, this is just saying SL times SL is SL square is SL. Right? So for example, this, if you look at it in terms of binary form, this would correspond to the composition law, where you can write down 1 comma delta and 1 comma delta prime, multiply them, write them down as a change the basis to 1 comma some new element. And so we come to the part that actually, so now that we have defined these rings, the question is, so what? Unless you have some sort of a computational approach to actually get explicitly what the discriminant of the ring looks like, there isn't a lot of use for it. So, and so we come to the Gauss lemma. This is the classical Gauss lemma, which says that the primitive polynomial is irreducible if and only if it's irreducible over Q. I should say a primitive integer polynomial is irreducible over Z if and only if it's irreducible over Q. So we try to look at this information in the context of the context of this particular theorem. And what this means is this information can be interpreted as the sequence O of L to the K when L is of rank 2 looks like Z, 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 Z till n minus 2, and then SL, 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 SL. So this particular sequence, which we know stabilizes to SL, looks is this form. So the fact that it is Z for a while and then immediately switches to SL is something that we see that this means that the Q generators, which is sort of pointing to this point, matches with the Z generators, which sort of signifies the start point of SL. This clean jump does not exactly happen for higher rank modules. So for example, in Bhargava's classification of quartic rings, what you will get is you'll get first Z, for 0 you get Z, for 1 you'll get Z, for 2 onwards you'll get some ring R1, R2, and 3 onwards you will get SL. So this is why primitivity does not correspond to the forms themselves being a minimal choice. You need a slightly stronger condition than the forms themselves being the maximal choice. And that stronger condition is what this particular Gauss lemma will allow us to determine what it should look like. So the general Gauss lemma is an effective version of this particular theorem, which will allow us to compute things. And this says that if rank of L is M and Q of L over Q is N, then SL stabilizes at Mn minus M. In fact, provided the prime is greater than N, then SL actually stabilizes at N minus 1 itself. So, no, this is just saying the valuation here. So this particular lemma allows us to exactly compute the discriminant of SL. I mean, this particular lemma is proved in the context of what we like to call a mini theory of denominators. And basically combining that with the understanding of this general Gauss lemma, we given any, let's say, if you give me a pair of degree 3 forms, you can actually compute the discriminant, define a notion of primitivity, which will always be an Ekadalian condition. And you can associate a degree 9 algebra to, let's say, a pair of cubic forms and so on. Okay. So as I pointed out, primitivity in pairs of ternary quadratic forms translates to O of L square equal to O of L cube. This condition is equivalent to O of L square equal to O of L to the 4, but we won't. The reasons we won't bother explaining why. And so if f comma g is a R of degree m, then we would define primitivity in such a way that we say that O of L to the m square minus 1 is equal to O of L to the m. The notable part here is the fact that this particular power is independent of the coefficients coming from the point L. It is independent of the point beyond its, it's basically independent of the point beyond the, let's say, the degree and this rank. It does not depend upon the specifics of the point, which is what sort of allows us this computation nicely. So since we are interested, since reciprocity theorems are about injectivity and surjectivity of these maps, the next natural question to ask is when can a ring be seen as an M-fine ring? So we'll point out some corollaries to the work that we have done. So one corollary is that every ring of integers in an extension of Q of degree less equal 7 can be represented as a two-fine ring of integers, two-fine ring. Every ring of integers, particular 6 is two-fine. If to do the m plus 1 minus 1 is greater equal L over K, and m is greater equal to, then OL is M fine over OK. And this is an interesting part. Every number field has a two-fine subring whose index is bounded as a function of the degree, independent of the discriminant. So the moment you go from 1 to 2, there's a lot of denseness that occurs, which is not there at T1 and Z bar. So we first, so just in the case of degree 4, we knew that every degree 4 point corresponded to a degree 2 curve, intersection of two degree 2 curves, or a degree 1 curve and a degree 4 curve. The degree 1 curve and a degree 4 curve can sort of be embedded inside the set of two degree 2 curves in a way that that's sort of a very small part. And so similarly in degree 6, what you can do is you can sort of look at all such threads, and all of those threads can be embedded into a larger thread, and that's the thread that we're discussing. And so this is the first theorem. This says that given such polynomials, 4 degree 4 polynomials, when do they cut out at a point of degree 6? So the answer is we can give explicit polynomials that say di, ei, and fi are explicit polynomials in ai, bi, ci. Whenever that is true, these four will cut out a degree 6 point. This is sort of the generic thread of degree 6. Okay. So using this, if V denotes the standard GL2 representation and W star denotes the dual of W, then to every rational point of Sim2 tensor Sim3 V star, one can attach a degree 6 ring. This ring is invariant under the natural action of GL2Z and that of Z cross Z. And the orbit space, based on a previous theorem, includes every sextic ring of integers. So the discriminant is also explicitly computable in terms of ai, bi, ci, provided I am allowed access to the denominators. We need these to be rational. So we are hoping to use this in a more general context, hopefully appropriately get slightly better bounds for degree 6, upper bounds for degree 6 extension of number field. Thank you.